Okay, welcome everyone. Apologies for the 5-minute delay. We'll continue on our policy gradient methods, which we started in our previous lecture. Today is the last day for which material will count for quiz 1. Okay, so no need. So what we're going to cover on Wednesday will be part of quiz 2. We are grading your homework 1. I mean, here is what happens in the beginning of the semester, because people still decide which courses to take. Sometimes it's very normal for your partners to leave the team. This is totally normal. Part of homework 1 is always like this. So we have given some extensions to those people. And as a result, your grading will maybe delayed because we want to show the grades all together. Okay, that's it. Okay. I don't have any more logistics to discuss. Yes.
Just let you know, in-person office hours is starting today, and the rooms are going to be posted on the website, and they're also on the calendar.
Perfect. So now you can go to find your TAs in person and discuss with them your problems. Okay. Okay. So we'll start from what we actually touched a little bit last time. I also received some pretty amazing questions last lecture during office hours. So I'll get back to those questions. We had your colleagues suggested that the way we, let's say, solved policy gradients as maximizing trajectory returns was a little bit misleading, because essentially what we did, we would not come up with new trajectories that would maximize those returns. The only thing we did is we'd have a collection of trajectories, we'll have the assigned returns, and we'll change the parameters of our policy to make trajectories with high returns more probable and trajectory with low returns less probable. Okay, this is what policy gradients do. They don't come up with new trajectories and how to connect different states and so on. They just look at the current trajectories, and the actions they actually seen in those trajectories, they make them more probable if the returns are high and less probable if the returns are low. Okay, so today's lecture will again, give this application of that method in playing Pong. All right, in playing Pong, and then we'll jump to actor-critic methods, and you will see how very naturally actor-critic methods falls from policy gradients, trying to minimize the variance of policy gradients by having this critic and subtracting it from the returns. That's all it is. And we will also see a very cool paper, very, highly cited and, popular on actor-critic methods that was able to scale up reinforcement learning across multiple cores and collect experience in parallel. That's it. So a very simple lecture, lots of fun. Yeah, so that's it. Let's start. So here is the game of Pong. That's what we said last time. And the actions are only 2. Either you go up or you go down. So it's a discrete action set and pretty also small. You get +1 if you pass your opponent, and you get -1 if the opponent succeeds. That's all. And we said, let's put down the architecture of your policy network. So this is a very important decision that we will need to do in every problem. Okay. And in my mind, at least, what I would do is I would take the image. Okay. And I may have taken also, let's say, 2 images, because I want to know the ball, which direction it goes. It goes up, down, you need, because a single frame is not enough to tell you the velocities of objects. So usually you need 2 or 3. If you remember in Atari games, we concatenated 4. All right. So I would take image, I would stack some previous frames, I would pass them through a CNN, I would do a pooling, I would spit out a vector. From that vector, I would put, a sigmoid, because the only thing I know is the probability of going up, because the probability of going down is -1 minus the probability of going up. And that's how I would build a network. But here, Andre, who is actually the author of the blog post from which the slides are coming, he said, you know what? I'm just going to make a fully connected network. I'm just going to take those pixels, make a long line, because my focus here is to teach you, how reinforcement learning actually works during policy gradients, and I want to be agnostic to the architecture. So this is what he decided to do. And I'll have 2 layers. And essentially, I have 1.3 million parameters. These are a lot of parameters that we need to estimate from experience. Okay. And then he said, and here is the big, we said this is very important. It's a huge illusion. It's very difficult for us to understand because we're so good perceivers that understanding there are three objects there, even this is non-trivial for the network. Okay, we haven't run an object detector. We didn't give to the network the idea that there are three objects. Okay, it cannot reason over objects. The only thing the network can do is reason over pixel values. Okay, that's all it does. It looks at pixel values in this long vector, which, by the way, if you show me an image linearized, I won't be able to understand anything. All right, because pixels that are nearby, and if you flatten it, they become far away. So it's really not the best representation for an image. Very difficult, but that's what it is. So we're gonna still manage to learn this from experience. Okay. Now a natural question you may have is there neural architectures that would be able to process the notion of objects, or that the notion of objects emerges, or that we can actually reason over them and so on? What do you guys think? Okay, yes?
CNNs have some inductive bias with spatial locality.
CNNs have some inductive bias, exactly the way you said it, of spatial locality, but do they have inductive bias of object-centricness and that the world is comprised of entities and so on? No, exactly. Other people, do you want that have heard from somewhere anything on this topic? Okay, so we will see later in our course graph networks. Graph networks operates over graphs. The graph here would be, for example, would be a set of nodes with their edges. Their edges denote relationships, and the nodes may as well be the objects. And you can rely in some outside, a hopefully awesome object detector to spit out the objects for you and track them over time. And then the only thing you need to worry is you have your tracklets, so now you have your nodes over time, and you only worry, look at how these objects look like, their features, and reason exactly what to do. And you will see, in fact, actually, that was the quiz paper that we had the very first time that we added papers on quiz 3. The paper that we added was about the policies being graph neural networks for stacking, and how this inductive bias actually allows you to learn much faster than treating those as long, sequence of pixels or CNNs. Okay, so yes, this exists. We're going to visit those architectures, and I can tell you that it's all about the inductive biases of your policy network, because the inductive bias of your policy network is exactly what is going to allow you to learn fast, all toddlers know, to be able to generalize to novel environments, to more objects, less objects, to background colors, and so on. So it's all about representation learning, okay? But this is not what we'll discuss this week. This week, we just remain agnostic and, we talk about the reinforcement learning methods. Any questions here? Okay, so our network doesn't see anything about objects. It only sees, those 6,400 numbers. And every now and then gets some +1, -1. Oftentimes it doesn't get anything because nobody loses, they keep playing. And then it needs to figure out how to place those 1.3 million parameters. So let's contrast reinforcement learning to something that we know, which is supervised learning. For example, supervised from the expert actions, okay? So how would supervised learning work in our case? Well, for every state, x1, x2, x3, and so on, for every configuration of the state of the game, I would have paired with, I would pair it with the corresponding ground truth action, the action of the expert, okay? And then my network would be trained just from maximum likelihood. I want to make the expert actions more probable. And here is a cross entropy loss that we usually use, and everything would be end-to-end differentiable, okay? Everything will be end-to-end differentiable. So unfortunately, we don't have those labels. So I need to discover those good actions from trial and error learning, for just playing and interacting with the environment. Okay, so we're going to do reinforcement learning, which means you try a bunch of stuff, you see what works, what didn't work based on the returns of your trajectories, and then you do more things that worked well in the future. Okay. So what do? We start with our network, we initialize the weight randomly and we play, and then we collect trajectories. And in some of them I will win, and in some of them I'm going to lose. And I don't know why I won or I lost. The only thing I see is the reward, okay? I don't know which actions were great in that trajectory and which actions were not great. And in fact, the longer the trajectory, the harder to essentially do this credit assignment. But the only thing you say is you can label trajectories as good or bad. And the reason this is the case in our setup is because the reward only shows up at the end of the episode. Okay, if we had rewards also sprinkled in different time steps, we'll be able to exploit that temporal structure. But here, there's nothing we can exploit because the reward comes at the very end. All right. So do you not have a clue which action was actually great or bad and so on? So here again, we lost and we don't have we don't know what happened, but we know that was bad. So then what I'm going to do is I'll pretend that all those green actions were good and I want to make them more probable. And I'll pretend that all the bad actions were bad and I want to make them less probable. Okay. And this is a good assumption. It's a super crude assumption. Probably there were some pretty awesome actions on those red trajectories that there was nothing wrong with them, but unfortunately I don't know who they are. So I'll treat them all as bad and all the green ones as good, okay? And by just collecting tons and tons of trajectories, as your colleague, I think, suggested last time, by aggregating, I hope that the good actions will eventually shine, okay? All right. So this is the policy gradient that we discussed last time. This is the probability of different actions and the reward of, if you remember, the sub-trajectory that starts for this action that showed up on essentially ith trajectory at time step t. And here you can put the reward of all the ith trajectory or the ith trajectory after time step t if you want to exploit temporal structure. And in our case, it doesn't make a difference because all reward shows at the end of the trajectory. Okay, so here is supervised learning and reinforcement learning side by side. All right. And in reinforcement learning, we actually do not have labels. So basically, we have to sample them from our current policy. And once we collect a bunch of trajectories, then we will maximize these terms as we saw, okay? And AI is the advantage. So, and advantage means how good is the particular action that I did over the general actions coming out from that state. Ideally, this is what you want the advantage to be. +1 means that it's something good, and -1 is something wrong, and I don't want to repeat it in the future. Is that clear, guys? Does this make sense to you? Okay, and while on the left case, my data set stays the same, and I just update the parameters through gradient descent and maximum likelihood, on the right, my data set keeps changing. I need to update my parameters and recollect trajectories and update my parameters and recollect trajectories. And I need to be iterative. If I don't iterate, there is nothing I'm going to learn. Okay? Yeah. All right, any questions here? So this is the end of the, yes, please.
Yeah, in this case, how do we pick a policy for the opponent?
Policy for the opponent. So the opponent can, well, in AlphaGo at least that we're going to see, the opponent plays also with the same policy as you. Okay? The same parameters that are shared with you and the opponent. Okay? And you only optimize for yourself. But as you become better, he also becomes better. We're also going to see that instead of playing against your latest parameters, theta, you can also be playing against your previous versions of parameters. Does this make sense? Yeah. So that you make sure you beat also earlier versions of yourself. That's it, I think. Yes.
But does it then help to collect the opponent's trajectories? Because it's following the same policy.
Yeah, so you're saying, so the same way you collect for your own policy, you collect, yes, you can aggregate them and collect all of them as one experience buffer. Okay. So this is policy gradients. So now what we're going to, yes, please.
I was wondering if it makes sense. So since we don't really know why something is good, something is bad, does it make sense sort of split it into two stages? One, we do this sort of training, and then this will take longer, but if we sort of then try to reason about why something was better or bad and try to induce that onto the next stage of training, does that make sense, or is that feasible?
Yeah, so the alphas are essentially trying to do that. They're trying to tell us if an action is good or bad, but alphas themselves are noisy. The alphas themselves depend on the trajectories you collected, the advantages, I mean, okay? Because the environment may also be stochastic, and something that normally could have been great, in this particular case didn't work out, and so on and so forth. Now, maybe what you're trying to say is the following. We'll see many methods that combine imitation learning and reinforcement learning, where imitation learning tells you what are good and bad actions, and then through trial and error, you're trying to improve upon the initial policy you learned through imitation, okay? So that would be two-stage. Now, another two-stage that also comes in my mind based on what you're saying is the following. You do trial and error learning, and somehow you come up with some golden trajectories. You say, oh, I really did really well here. I mean, look, I passed the Atari game level 1, the fastest I've ever done before. Let me save it and make sure I imitate it in the future. So yes, so right now we have an extremely naive way of using experience. We need to realize that good experience, meaning experience where the advantages are positive, good actions are much more rare than bad actions. Things that nothing, you always lose. You don't actually figure out how to finish the level. So we just throw everything into our experience buffer. The truth is that experience with positive rewards in difficult environments, like, for example, games where the reward is very sparse in time, are very, very rare. And once you actually update them, you better do something better than that, chopping them into state action, next state reward, and throwing them into experience buffer and then stop resampling, correct? And yes, we will exactly discuss those methods. For example, one method that comes to my mind is Go Explore, that showed that if you do a more intelligent use of good trajectories, you can actually not only do much better than any other programs for Go Explore, but with also some domain logics, you can do much better than humans in that game. While we know that if you try to apply the reinforcement learning method that you just know already, DQN and policy gradient and so on, I can tell you that you will just be sampling and getting zero rewards no matter what. So you will have a very, very long cold start. You will never be able to kick off useful learning, okay? Is that clear? Okay, yes.
Also, since you're already maintaining this sort of an experience buffer, if we also maintain a good experience buffer of sorts, so can we also make a epsilon imitation strategy that whenever we're sampling labels, epsilon amount of times we sample from what we know is good.
Yes.
And the other times we just randomly sample.
Great. Yes, we will see exactly these things in the future. Yes, you are absolutely correct. They call it self-imitation learning. So as if you discover good things and then you want to imitate yourself and bootstrap yourself. And this is also how we do, if you see. I mean, we fail and things go crazy when you try to open, let's say, a jar. And you don't try to replay your bad experience. But once you figure something out, then you really, really use it and explore around it and really try to squeeze as much as you can out of it, correct? So yeah, these are very, very nice intuitions. Questions? Okay. Great. I'm very glad you guys suggest our future topics that we need to be looking into. Now, what I'm discussing next is how do we go from policy gradients to actor critic methods. And the reasoning is extremely simple. This is the policy gradient we'll put down. And it is unbiased indeed, which means that in the limit of collecting tons and tons of trajectories, capital N is the number of those trajectories, we'll be able to have the correct estimator of the gradient. Unfortunately, it is super high variance, and we'll try to improve its variance. And by the way, I have already explored temporal structure. RUCG has a subscript T, all right? So this is not going to be the answer to how we're going to move forward from here. Okay. Our goal will be to minimize the variance of our estimator. Let's see how we can do it. Now, I have the intuition in a few slides from now, but let's imagine that we want to subtract from that estimates G some constant b, okay? Some constant b, the same constant everywhere. Now, the first thing that we want to see is that actually if you add minus b there, yeah, so you have this new term, the red term, actually, you will see that, you know, on expectation, that term will go to 0. So you don't need to worry about it. It seems that it doesn't matter. You can take any random number b, constant, subtract it from your returns, and actually the results are going to look exactly the same, okay? And why they're going to look the same? Well, let's see. Because you have here the expectation over trajectories of that grad theta log p theta and the b, which is the second red term, all right? And the log can actually be written in this form. We know that, okay? And then this and this can cancel one another. And then you have that constant b, you can keep it out, great. And, you know, we know that the derivative is a linear operator, so I can take this out of the sum. And this is actually equals to what? 1. And the gradient of this is 0, okay? The gradient of a constant is 0. So now I understand that you say the last thing that I will come up with when I wake up in the morning is to subtract the constant b, but just hold 1 second, okay? So we're still unbiased, everything is good so far. Now let's see what we can subtract. We can subtract some constant, and that would be, for example, the mean of all reward trajectories, okay? We can subtract something that depends on the time step, or you can subtract something that depends on the state. And exactly subtracting something that depends on the state is an actrocritic method. And here is why this is important, okay? Consider that there are two states, S1 and S2, in our state space. And consider that the rewards of all actions in state 1 are around 3,000, and the rewards of all actions in state 2 are minus 4,000. And why this is the case? Because unfortunately, some states are better than others, right? In some states, it's much better not to be than in other states. However, when you're optimizing your policy, your goal is no matter in what state you show up, you need to make sure you pick better actions than average, okay? So you don't say, oh, I want to pick the actions of the state with 3,000 mean average more than the other actions. No, your goal is at every state, you need to be playing competently. Okay, even on states that on average are actually not that lucky. Okay, so here are those states. All right, and now the G, which is the essentially the return of a particular action that shows up in the trajectory, may be 3030, and some other maybe 2970, and so on. But the value of a particular state, as you said, the value of state 1 is just much higher than the value of state 2. And what you care about is not actually the return. What you care is the advantage. And this is exactly the same term we used in our policy iteration when we were trying to think, okay, in every state, I want to go and find actions that have policy advantage, positive advantage, which means if I switch to them, I will actually be doing better, which means what? That their Q, S comma alpha of that particular alpha is higher than the value of the particular state. That's all I care about. Do you agree? So, and this is precisely what we will be using in terms of, instead of G. We're going to be using the Q of that action minus the value of the particular state. Now, the Q of that action, you can, we don't know it, and you may as well approximate it with the returns. So now you have the return minus the value of particular state. Is that clear? Okay, let's continue our reasoning here. Yeah, so our goal is to select the right actions across both bad and good states, okay? Now imagine that you have a baseline, and this baseline is state conditioned. So the baseline of this particular state S1 is actually the value of that particular state, 3,000, and the baseline of S2 is minus 4,000, and you subtract those values from your returns. So then, so now it's much clearer, okay, that some actions will have positive advantage, which means the policy gradient will try to make them more probable, and some others will have negative advantage that will try to make them less probable. Do you see? You don't want to make less probable the actions of the bad states. You want to make less probable the actions that have negative advantages that will lead you to do worse than average. Is this reasoning a little bit clear? That's why we will be subtracting the value function of the particular state from that red term. All right, so instead of using G, we're going to using G minus B. And you know, a state condition baseline, okay, is what? Is the value of that particular state. Okay? Is that clear? Here it is. So exactly like in our Pong slides, we care to come up with advantages for actions. How can a quantity that tells me how much better is that state on average, how much better is that action on average from other actions I can take in that state. And on average, across all other actions I can take in that state is what? Exactly the expected return of that state, which is the value of that state. Okay? And here is the subtraction term. And now a very reasonable thing would be, how will I be estimating the value function? Well, the same way you were estimating the policy gradients from trajectories. And you can do Monte Carlo estimation or TD estimation. So now the important thing is you need to have another network, not your policy parameterized by parameters theta, but a value network parameterized by parameters phi. And you will initialize those phi's randomly. You will collect trajectories, exactly what the trajectories you collected for policy gradients. And then you will, for every state, you will be regressing against the empirical return. Okay, which is the return of a particular state, the sum of rewards you would get from that state onwards of your trajectory. This is precisely what we were doing in the Monte Carlo lecture. Okay, who would like now to tell us an alternative? I want to be estimating value functions from experience. I know how to do this from my Monte Carlo and TD lectures. Who would like to tell us the TD version of that value estimation? So we said, if you remember, Monte Carlo does not bootstrap and TD bootstraps. You remember? Yes.
Can we fix phi to be some old version of our current parameters data, update data, and then replace phi with the new version of data, the way we did W minus and W?
Right, but the question is the following. If you see here, this is a least squares problem, is a regression problem. Essentially, you train your value function like a regression. Very simple. And a regression requires targets. Somebody needs to tell me, this state has what value that I need to regress to? And here our estimates come from sum of rewards onwards from what that state shows up in the trajectory. This is the Monte Carlo target. Who would like to tell us what is the TD target? By the way, phi argmin, guys, what exactly does this mean? It means gradient descent. Phi new equals phi old plus alpha, which is the learning rate multiplied with the gradient and so on, or minus, because here we have, we minimize the loss, essentially, we don't maximize objectives. Is that clear? Okay, yes, you want to say the TD target?
So, yeah, the Monte Carlo, if you look at the full path of rewards, TD just give the reward of the next step plus or the reward of your step plus the value of the state that it could go to.
Exactly. Exactly. And for the value of the state that you go to, you use exactly your V phi. Exactly. Okay, great. So here it is. This is exactly what your colleague said. Immediate reward plus V of the next state. And if you want, you can use also n step TD, which means, immediate rewards for n steps plus gamma to the whatever power of the V of the after state and so on. Yes?
Are we not discounting the...
Yes, I don't know. I think there's a typo. I think there should be a gamma there. Okay. Good point. Is that clear? Yes.
You will discount on the previous slide also, right? Getting the NC return from time t.
Yeah. So this is an episodic task. And we actually just summary words. I mean, you can also discount them if you like, but usually you can also not discount them. I mean, both are fine. Both are fine. Both are okay. Okay, so let's try to put everything together now. Let's try to put everything together for actor-critic methods. The important thing is to know that we have two networks, the actor and the critic. The actor is the policy network, and the critic is the value function network, and you can keep them separately, or you can actually have them sharing the backbone and having two separate heads. Why is it a good idea to share the backbone and have two separate heads? Who would like to say something? Yes? Multitask learning, meaning that the features in the backbone are useful for both tasks because these are very related tasks. How to play and how good is a particular state. Yes, that's right. Okay, so let's see how we're going to do it. So we have two sets of parameters, the critic parameters and the actor parameters. Okay, and the pseudocode looks like that. We'll initialize both of our networks randomly. We will be sampling trajectories by deploying our policy in the environment. We're going to be fitting value functions through regression using either MC targets or TD targets. We will be computing the advantages using those value functions, which are the returns of every action in every trajectory minus the value of the particular state. Okay, and we will forming policy gradients, and then we'll be updating the policy network as well. And then now we have a new policy, we repeat. Okay. Are you okay? Yeah. So sample returns, so this is similar to what we said earlier. So those alphas are essentially a Q estimate. I want to figure out the Q of how good is a particular action going forward. In fact, the G minus V is exactly Q minus V, which is precisely the advantage. All right. Now, some people also, instead of G, they will plug the Q value there instead of the sample estimate. And so you will see how we're going to do this exactly. Okay. So basically, G return, this GT of I, are essentially estimates of the Q function, correct? All right. So essentially, what type of estimates? Monte Carlo estimates, because we don't bootstrap. We just take all the rewards. Instead of that, you may as well do bootstrapping also for the GT of I term, which is the following. You can compute a Q network that actually spits out exactly those Q estimates, all right? And you can have a learned approximation of the Q, correct? And let's see how this is going to be done. You can be using the same V phi, the critic that we just said, to actually have a better, let's say, estimate of that G. And what is a G? G is, so far the way we discuss is sum of rewards that you showed up in your trajectory. That's what precisely GT of I. That's the definition, right, of GT of I. You go to the ith trajectory, you go to the tth time step of this trajectory, and you sum the rewards from that time step onwards till the end of the trajectory. However, this is a sample estimate of what? Of the Q. In expectation, what are the sum of rewards I will be getting from that stage and action? That's all it was, okay? Now for Q, I may as well use the tools that I know from TD to form a biased but less variance estimates of that Q value. And what would that be? Well, Q essentially, you can do exactly the same, this approximation. I can take sum of immediate rewards, immediate or more, depending if I use n-step TD or zero TD, TD0, and then the value of the next time step. Okay, so now, essentially, I'll go to another, what I call advantage actor critic, okay, where alpha, the advantages of actions, the only thing that changes is the advantage, how I estimate the advantage. Instead of being G minus V of the particular state, of the same state, is immediate reward plus gamma V of the next state minus the V of the present state. Is that clear? Okay, let me repeat because this is very important. And now, because the paper we're going to see now uses exactly this code, this thing here is essentially a state condition baseline. If you have an action in a particular state ST, you subtract the value of the same state because you want to make sure that you compute the advantage of a particular action, not how good or bad this state is. All right? So we all understand now this part. Now, what this does is essentially it's a TD target for Q of for Q of that action AT of I. All right. Before it was a sum of rewards from that state and action onwards till the end of the trajectory. This is another estimation. That was the Monte Carlo estimation of that. This one is the TD estimation of that. That takes the immediate reward plus gamma V of the next state. Okay. Now, the good thing is that both this term as well as my state condition baseline both use the same network, V phi. Who would like now to tell us another estimation for the advantage that doesn't use the TD0 for this Q part, but uses the TD1 or TD2 or TD3, you know, like n step. Yes?
Reward of ST80
Mm-hmm.
plus discount factor, reward of ST plus 1, and the action will take using pi, I think.
Very good. 1 second. Let's think about this. Now I have my trajectories ready. You see? So you know the action. The actions are given to you by the trajectories. It's very simple. You just fit the trajectories into the equations. So yes, let's continue. So I think what you just said is this reward plus gamma are ST plus 1 I, comma?
AT plus 1 I.
Exactly. So what is AT plus 1 I?
The action that we already sampled, because we already sampled a full value.
Right. From the ith trajectory at T plus 1 step. Exactly. And then?
And then if you do TD1, now we can use gamma square.
Gamma square?
Plus value of ST plus 2 under.
Yeah. Multiply. Yeah, exactly. That's it. Okay. So we have essentially, this is our advantage for a particular action in this state, which is an estimate of the Q minus the estimate of the value of a particular state. That's all. And you can form your favorite estimates for Q. You can put returns, which is no bootstrap. You can use TD0. You can use TD5, which is exactly what we're going to see in this next paper. Yes?
I was wondering the baseline that we're subtracting, is there any reason why we never scale it to anything? Will it not, I mean, since we're taking the V estimates as well, do we not worry about it, if, I mean, blowing up or vanishing? Is that not a...
Yeah, so what is this? This is the value function, which is the expected reward from a particular state under policy pi, let's say. That's why there is also this pi here. It doesn't, that depends and scales with your rewards. If your rewards are in the scales of hundreds, it's going to be around 100. If the rewards are around thousands, it's going to be around thousands. If the rewards are minus 100, it's going to be around 100. If the rewards are between minus 1 and 1, there's going to be in that range as well. Now you can rescale your rewards, make sure that, look, my value estimates, you know, it's a neural network. I cannot be spitting crazy numbers like 3,000 and so on. I need to standardize my values. Absolutely, yes, you can do that. This is a standard thing we do. Whatever you do in a standard regression task, you can do here, okay? But the reason we don't put any gamma here is because I care to know how good is a particular action, ATI specifically, over other actions in the same state as I of t. You see? So I want to say the goodness of an action minus the goodness of the specific state. The goodness of an action is Q. The goodness of a state is V. So it's Q minus V. And this Q is, this what you see here is a Q estimate. It's reward plus gamma. Yeah.
I was just wondering, so if we do scale it, would that sort of mean how aggressively we want to calculate an advantage and also?
No, it's not. The math doesn't work at all like this. It doesn't mean anything. Well, here, the way we motivated this subtraction is exactly because we want to say how good is the expected return I'll get from this state doing action over the expected return on average from that state. And if you look at the recursions of returns, which are just sum of rewards, you will see that you just have this extra reward of run that action over the other rewards from these other actions. You see, we're just summing rewards. We're not coming up on our own with, let me cook up something. It's just that's how the addition of rewards essentially turns out to be. Yes. What is your question?
So is the point where are we doing TD0 to reduce variance?
Yes. That's all why we're doing TD0. Yes.
Okay.
Otherwise, you can be using G.
Like greater variance.
Yes, that's all. Okay. Okay. Yeah. So now you need to code this up in your homework too. And so here's my question for you. Let's say I tell you, you guys need to code this up. You're not allowed to use the internet. Okay. What would you type in your PyTorch or TensorFlow to get this term, to get this gradient to work? Okay. That's the question now. Okay, so auto differentiation packages, essentially you write expressions and they automatically generate the gradient of these expressions. Do you agree? That's what they do. So now we need to think, what is the expression that if I write it down and I can assume my trajectories and everything, okay? So you've already collected your trajectories, you've done this part, you went to a simulation environment, applied your policy, let's assume you figure out how to work with the simulator and so on, you initialize your policy, everything was good, you were able to train your value function because it's just regression and you guys know how to do regression, correct? Now you're ready to do that part, okay? Now this is the only thing that is a little bit newish. So what would you guys do? What would you type in your TensorFlow? What expression would you, yes?
You can just type the same thing without the gradient step and then do a dot backward of that.
Yes, which is this double summation, exactly the same, but without the gradient. Other suggestions? Yes.
We want the gradients. So when we're updating the actor, we do not want the gradients to flow through the critic, right? So we have to freeze when we calculate a pi function. We do not want the gradients to flow back all the way into critic when we are updating the.
Okay, so now it says, well, but yes, but let's discuss a little bit. Well, sure, but the critic has its own parameters, phi. And
we have a shared backbone, so
yes.
If we don't freeze it, it could flow.
Well, but here's the thing. If me and you have a shared backbone and somebody takes gradients over me, your parameters are also going to change. So because we have a shared backbone, you can freeze the head because you have your own head. That's fine. But if I propagate, you will also be updated. That's the whole point of the shared backbone. But this is a good point. It's a good thing to worry. So what about the suggestion of our colleague?
That seems correct.
Yeah, that seems correct. So that's all we're going to do. We'll collect our trajectories, go type that expression here. These are all going to be whatever you can leave them around. Let me see. Well, I see. So now what you're saying is I want to put stop gradient here, right?
I've seen codes for SST, TD3, DDPG, they always freeze.
Yes, yes. So stopping gradients here so that we cannot update the file so that, this thing goes up, right? Is this what you're saying? Yeah, I think, yes.
I mean, if we make a Siamese sort of a double-headed network with a shared backbone, if we take a gradient over head 1, head 2 won't be updated. It will only update the shared.
No, head 2, for sure, this is not going to be updated, absolutely. But I think, yes. Let's think.
I'll have to look up an implementation to be sure what. So you see that the value is coming out of head 2,
right?
And you essentially have A that is computed using head 2.
Right.
So I don't know.
So I think what you said is the following: if you dump this expression, these are not constants, right? Yeah. These are not constants. Then this guy's going to try to do chain rule here, and these guys have some parameters that need to be differentiated. Let's say with respect to. And we don't want that. We want semi-gradients. We want this to be considered constant so that the gradient only shows up on that term. Do you see? The chain rule works like this because these are constants. Okay, I think this is what you're trying to say. And I think this is the correct intuition. Okay. All right. Yes?
So So going back to the like advantages,
Going back to what?
like the advantages.
The advantages.
Step 3.
Okay.
Like, we could still have that like all the advantages of like a state and like an action pair, like even after subtracting the value of the state, would be like negative, right? Like if like no.
Yes, they can totally be negative. The advantages. Some are going to be positive and some are going to be negative. Absolutely.
So like what's like the benefit of like subtracting b pi as opposed to just like making it like mean 0, for instance?
But exactly, subtracting v pi exactly wants to make the advantages to be centered at 0, so that the actions that actually I want to make more probable have positive advantage, and the actions that are less probable has negative advantage. That's exactly the point of subtracting v pi of s.
So like if I'm at a state where like no matter what I do, like I'll immediately like lose 1,000.
So I have minus 100, you see? Exactly. So it 0 centers the advantages.
So I guess it'll still 0 center.
Exactly. That's exactly what we want to do. Yes. Great, guys. So this is very good what you said. Very good point here with because the chain rule, better differentiate only the log p theta of whatever, not the advantages. Okay. Great. So let's see. So now here we go back to our term policy iteration, and now we'll see how actor-critic method is also an instantiation of policy iteration, as many other methods that we're going to see in this course. Why this is the case? Well, what happens in policy iteration? You initialize your policy, you deploy the policy in the environment, get the experience, then you estimate and identify advantages. You remember what we had said when we were in tabular methods. Go in every state, and if you see an action whose Q is higher than the V of that state, switch to that action. That's all we did, if you remember. So now we need to be estimating those advantages. An advantage is when the Q of that action is higher than the V of the state. It is that simple, right? It's very concrete. And that's exactly what we formed. And then we changed now the policy. Back then they were switching to change those actions because we had tabular methods. But now the only thing we can do is we can update our policy parameters theta to make the actions with the positive advantages more probable than the actions than the negative advantages. And we have a new policy, you deploy it in the environment, and so on and so forth. Is this clear? I think it's pretty clear given how many times we discussed it. All right, so now real quick, I want to say something that says the following thing. In actor-critic methods, the way we have described them, they are own policy methods. You use the data of the current policy to improve the policy. As you see in that blue, is we always deploy the present policy theta. And I mean, this is very, very, very costly because each time you update a little bit the parameters, you need to go and collect new experience. So here is few slides that are going to be motivated more on Wednesday of how you can actually use experience from older versions of your policy, so experience collected from previous thetas before your gradient updates, to actually still use them in the present policy and update the new policy gradient. Okay, so how can we do that? Well, what if we use importance sampling? Let's see. So here's expectation where trajectories are sampled from some policy with theta t. And this is actually the policy objective we have put down earlier that we said we want to optimize. So one thing I can do is multiply and divide with the probability of a previous theta old. Okay, do you see? So this is always what we do in importance sampling. We multiply and divide with a, density function that we can sample from, p theta old. In fact, I have collected already trajectories from p theta old. And to make sure that the approximation, there's no approximation and, things still are, accurate, I need to divide with the probability of the items of the domain, which are here the trajectories, under that p theta old. And we have now these ratios, right? Of these ratios of the probability of the trajectories under the new policy theta that I have and the older theta old, correct? So let's take gradient again under this formulation. All right, here it is. I'll take the gradient of that thing. And okay, so it's going to go inside the expectation. Now it's going to go next to my gradient theta p theta of tau. And this is totally okay. Now, what we did here is we did the same trick we had done before. Yeah. We divided and multiplied with p theta of tau, and yeah, and now essentially the one shows up the log, and now we have this essentially the same thing as before. We have still a likelihood ratio estimator, but now we have this extra ratio of p theta of a trajectory divided by the p theta old of the trajectory. Do you see? So exactly the same as our previous policy gradient with these extra ratios. Now these ratios unfortunately are pretty nasty. Does anybody remember to tell us how these ratios look like in practice? What is a p theta of a trajectory and p theta old of a trajectory, the division of this?
Yeah, I think there's two components that are involved. One is your policy, another is the dynamic.
Yeah, okay. So you're saying that the probability of a trajectory is a big product of dynamics per time step dynamics and probability of actions? Okay. And then?
And you just like expand them.
You expand them, yes, but here we have a fraction. So we have two policies. The dynamics, we do not know them, but it's the same for both policies. So what's going to happen? They're going to cancel out. So essentially, you just have this fraction of very long products. Okay. Okay. Now the gradient. Now, if you take that here and evaluate it at theta equals theta old, then you get exactly the same form because p theta old divided by p theta old cancel. Now let's go back to what your colleague just said. Here is the probability of a trajectory. Here is this fractions. Is exactly what he said. That there are dynamics and probabilities of individual actions, and the dynamics cancel out. So essentially, I have this, fractions of products, and then I can plug them into my whatever formulation. And the truth is that I can also use causal structure if I like, which means I have the actions, and I may as well, make sure that here the probability of a particular action has only to do with the trajectory segment leading up to that action, and the rewards, how good an action is, only have to do with the rewards I get after that action, actually. Okay? So this is what you get. This is the off-policy, policy gradient with importance sampling. And unfortunately, despite the fact that the math is actually kind of easy, is not a very useful formula. And the reason it's not very useful is because these terms are actually very nasty, because there are, long products, and each one of those action probabilities can be very, very tiny. So this, essentially, this term can either explode or vanish depending on where these tiny probabilities show up on the denominator. Okay. So despite the fact that this is precise and this is actually super accurate, and we haven't done absolutely any approximation, and now if you use this formula, you can use earlier trajectories, okay, to form your policy gradients. That's what we achieved. Yes?
When you say earlier trajectories, just the fact that theta old has the information of earlier trajectories, or how exactly is that?
Right, great. So no, very nice. So this expectation now of trajectories is under p theta old. So you will be using trajectories that you sampled under your old policy. Do you see? So, and because they're under the old policy, you need to make sure that you account for that change using these super long products. Okay. Yeah, unfortunately, this is not very useful. That nobody actually uses that. Okay, nobody uses that because it's actually, as I said, it's not very stable. It's not very stable. So instead, we will do approximation. And you'll see now how simple is the approximation. To motivate the approximation, we will go back to our objective. Okay, is u theta, which is the expectation of rewards of trajectories where the trajectories are sampled under our policy. And we will expand it in the following way. We say this objective can be broken into different time steps. And at every time step, I have an expectation under states sampled from my marginal state distribution, how much time my policy spends on a particular state. And then another expectation over actions that my policy samples from that state and reward of that state and action. Do you agree with this alternative writing? You imagine that you have a horizon capital T, all right? So this expectation of the trajectories can be broken into expectation over states and expectation of action sample from every state. Now, why would we never think to write this in the first place? Because this is impossible to compute. How I'm supposed to know how this is the marginal state distribution, how much time my policy spends in a particular state, how probable is a particular state under my trajectory. This is pretty not easy to compute in the first place. But anyhow, let's assume it's okay. Now let's see. So let's use important sampling now for the state and action sampling, okay? So here I have states and here I have actions, all right? So here is expectation over states and here's the expectation over actions. And here is the state marginal distribution of my old policy and here is my old policy itself. And look, I need to now, correct using those ratios. This is the probability of a state, the state marginal under the present policy and the state marginal under the old policy. How much more probable is the state ST under the present policy over the old policy? And then here is expectation over actions, the probability of an action under my current policy over the old policy. And I want to ask you guys, which one of those ratios are easier to compute? Oh, sorry. Which one of those ratios you know how to compute? And as whom we know theta and theta old, right? We know our present policy and our older policy. Do you know how to compute this one? Who doesn't know how to compute this ratio? Who doesn't know how to compute this ratio? You do not know. Does anybody know how to compute the blue ratio? How we're going to compute it?
It's just like the product, right? In the previous slide, the probability of the probability of it getting to a state.
Yeah.
Could you store counts for the state?
Sounds pretty difficult, given that the states are continuous, okay? And yeah, it's not that easy, right? So, but are you comfortable with the green ratio? Okay, so everybody is comfortable with the green and nobody is comfortable with the blue because it's just really hard to compute. Yes?
Yeah, so for the bottom part of the green, how do I know that? Because do I store the O?
Yes, I have the parameters. I have my neural weights from 10 iterations ago. I have my theta old, okay? So you can feed an action to your policy and compute, you know the state, you feed the ST into your old policy and compute the probability of the particular action.
Yeah, because I was thinking about experience replay. You got a bunch of stuff in your replay buffer. There's like 100 iterations before. Do I need to like store all the weights before?
Yes, you need. If you want to use the older policy, then you need to remember its weights. It is not that terrible because you want to be able to evaluate to know how probable your actions were. Okay, but that's very easy. That's not that difficult. So in any case, now here is the interesting thing. We're just going to get rid of the blue. We're going to approximate. It looks super scary, but we're just going to approximate it. So we'll throw it away. And now here's what I have. Okay, very simple. An expectation over essentially state and actions, which means an expectation. My parameters. So that's all. These are some little math. And do we know how to optimize this objective? Yes, of course we know. We'll take policy gradients, right? So here it is. I'm just going to take the gradient and I'm going to do all the tricks that I have done many times before. Here, multiply and divide with p theta. And this is the grad log p theta. And here is the ratio. And look what we managed. We got rid of the long products. Now we just have only the present term. Pretty great, right? So what was our assumption? Our assumption is that, you know, my policy changed, but you know what? Theta and theta old are not that far away from one another. So the marginal state distribution didn't change that much. And actually that ratio was 1. Okay? So the probability of actions per state change, because the policy has changed, But the visitation state distribution doesn't change that much. Is that okay? All right. And now we are going to the last 15 minutes of the lecture, which are very fun. And we're going to see a specific paper, which is part of your required readings, A3C and A2C. Okay, these are called. So here is, we're going to motivate what is interesting about this paper. Well, the truth is, to be able to train policy gradients, you want your gradient updates to be decorrelated, okay? But this is not the case if the data arrives sequentially, okay? If you have one agent that actually sequentially traverses the environment, and we said that, we actually discussed about this in DQN, and then we said, oh, we're going to have these big experience buffers and so on. But these experience buffers assume off-policy training, okay? Because you should be able to sample experience from older policy to compute your updates. And unfortunately, this limits reinforcement learning to off-policy methods, since the data from an older policy are used to update the weights and so on. Now, here is what we're going to do. We're going to throw away experience buffers, and instead, we will have multiple agents that parallelly collect experience in different parts of the environment. Some near to the cave, some on top of the stairs, and so on and so forth. All right? And because you're in different parts of the environment, then the visuals, the images are going to look different. So the experience will be decorrelated. And so I'm going to have multiple threads of experience, one per agent. Each will be exploring different parts of the environment and contributing experience tuples. And they can have different exploration strategies also and so on, or they can all use this very not intelligent epsilon greedy exploration. And now you can train on policy using our policy gradient methods, okay? So we'll go back to our actor critic. And now instead of having one agent exploring the environment, we have multiple agents exploring different parts of the environment and contributing experience. And this is the idea of a distributed reinforcement learning, right? That while there is a global network that is the actor and the critic, okay, there are multiple workers that collect experience. The most costly part is the experience collection. That's why when we say, oh, this RL method is really inefficient, what means is it requires enormous amount of experience. So the better you parallelize, the more you parallelize, the more experience you'll collect, the better your method will do, okay? All right, let's see now the details. So how these multiple agents are going to be coordinating between them. Yeah, so two things can happen. Locking and no locking, which means the following. Either all of them will have identical versions of the parameters, or they're going to have slightly different versions of the parameters, and they don't need to each one to wait one another to take a gradient, okay? So now what happens is that, as we said, there is this global network with the parameters for the actor and the critic, and every worker will be resetting to that global network, and then the workers will be interacting with the environments, and they will be collecting the values and the policy laws, and then the worker will be collecting the gradient and so on, and then we'll go and update the global network with the gradients, okay, that it computed. So I'm not going to go and average all the gradients from different agents. I'm just going to, take now this gradient, take this other gradient, and so on, and different gradient vectors will be contributed from different actors, and these gradients are going to be decorrelated because they're all going to come from different parts of the environment. Any questions? Okay. So this is the pseudocode. So let's see if we can recognize in that pseudocode pieces that we can relate to and we are already familiar with. So here it says that we have first of all, two thetas, a theta and theta v. So this is the actor and this is the critic, okay? And these are the global, and every thread is going to have its own copies, let's say, of those parameters, theta prime and theta prime v, okay? We reset the gradient vectors, okay? Now every worker, every thread will copy the global parameters right here. And then what it's going to do is going to start collecting experience, essentially deploying the policy in its own subpart of the environment and collecting rewards and seeing the next state and so on and so forth, okay? So, And then what do you compute? They will be forming TD estimates for the Q, and they're going to be using, of course, the state condition baseline, and I'll show you exactly how this works. So essentially, let me show you. So here you copy the weights, here is you're computing the rollouts, and here are precisely the advantages, R minus V, okay? So if your action I on state SI, you better subtract the V of the same state SI, okay? Is that clear? Now the question is, what is R? They have this complicated way of computing R, but basically if you run the code, the R essentially is, this is essentially the approximation of the Q. The R3 for the state 3 is immediate reward plus gamma V of state 4. And the advantage of the third action is essentially this thing minus the V of state 3. You see? Is that clear? Okay. Now, so here I gave an example of a trajectory that has, let's say, 4 states long. It's 4 states long. So is very similar to what we discussed with TD methods, that close to the end of the trajectory, of course, you don't have the bandwidth to take n steps on your immediate rewards. You just take whatever is available, okay? You take here, for example, 1. Now, for the second state, you take R2 plus gamma R3. For the other, we'll take R1 plus gamma R2 plus gamma square R3 plus, and so on. Is that 100% clear? Okay. Is this clear why this is an advantage? The approximation of the Q minus the approximation of the V? Okay. Great. So here is the learning of the critic, guys, which is a standard what? What does anybody want to say what these people do to compute the critic gradients?
Problem like we saw.
Yeah, this is just taking gradient descent on the regression problem, exactly.
So n-step TD, right?
Yes, this is n-step TD, exactly. Exactly. Okay, so this method is called A3C. Now, do you have any other questions here? I think this is what you will need to implement, but maybe without multi-threading, I'm not sure. Some version like this you're going to need to implement. Now, the A2C is when essentially there is locking, which means the gradients of all the workers are averaged and the central neural network weights are updated. You see? So it's not that every agent goes and with its gradient vectors update the network weights. No, it's everybody contributes gradients, the gradients are averaged, the global network is updated, and everybody gets exactly the same weights, okay? Yeah, now you will see when you are implementing, so here is a small trick, when you will be implementing this method, you will find this, and if you read carefully the paper, you will find this sentence, okay? Where we were taking policy gradients, we found it advantageous to also add the entropy of the policy to the objective for improved exploration. So essentially, you take your policy H of P theta is essentially the entropy of the policy. So you take a gradient to make sure that the entropy of the policy is high. Why? You want your stochastic policy essentially not to collapse, to be able to keep improving and put, non-zero probability to many, many different actions, right? This is very, very important for exploration, okay? Yeah, so here we have stochastic policies, so we just sample from the stochastic policy for exploration. And since we're doing that, we want to make sure that the entropy of the policy stays high, okay? So the policy does not overcommit. Now, next week, we'll see maximum entropy reinforcement learning, where maximizing the long-term entropy of a policy will be essentially side by side as part of our objective. Not only will we want to maximize external rewards, but we won't be able to have our policies be as stochastic as possible. Okay, so if multiple policies can maximize rewards, we want to be able to have high probability across all of them as opposed to committing in one of them. This is not it. This is not maximum entropy reinforcement learning. This is just a very greedy way of maximizing the entropy of the policy of the particular time step. We'll make the connection between that hack and the maximum entropy reinforcement learning next week. So yeah, so I think I've already discussed about how actor critic is a policy iteration. And I think, yeah, and that's the end. That's the last word. Yes, please.
Yeah, so when there's multiple agents, they all have the same weights, but they sample different trajectories because of this stochasticity where you're sampling from.
Yeah, no, actually, this is not only the reason, because each one of them is in different part of the environment. So you spawn them in different parts of the environment. That's why they have decorrelated experience. Yeah. Other questions? Yes.
Would you need to decay that data for that feature over time?
Which theta?
The beta.
Oh, the beta. Yeah. Yeah. So I don't think they did that. I'm not sure they did that. But there are ways to automatically adjust the schedule between how much you value you weigh the entropy term and the task reward in the objective. Yeah. Other questions? Okay. So you're free to go. We have office hours here, so please come to ask your questions.